Good morning, everyone. Just see a couple more people just logging on, so I'll just give it another minute and then we'll begin. Okay, it's 10 a.m. Thank you everyone for joining me for our final webinar of 2019. This is webinar number 5 in the Focus on Food series, and today we're looking at shelf life testing. Obviously, this is quite a large and complex area, so today's webinar will provide an overview of the key concepts around this important subject. In today's presentation, I'll begin with a formal definition of shelf life before moving on to which tests are relevant, which storage conditions to use, and how the interaction of all of these can help when setting the product's shelf life. With such a wide-ranging and complex subject, I won't be going into too much detail on every aspect of shelf life testing, but hopefully we'll provide some examples, some links to additional resources, etc., and cover the main points. I'll begin with a definition of shelf life, followed by a short explanation of the differences between best before and use by, and their implications in terms of testing. So there are and have been many definitions of food shelf life in the scientific literature. It can best be summarized by one of these statements that I like. It's shelf life is a period of time for which food remains safe and suitable for consumption, provided it has been stored according to the stated conditions. So what I like about this statement is that it includes the key areas of concern for food, which of course is a biological material and therefore deteriorates over time. So primarily, is it safe to eat? If it's safe, does it also retain all of the key characteristics of flavor, appearance, taste, and quality that it had when purchased? If it does, is the stated nutrient profile still as described on the label? When one of these elements, safety, spoilage, or nutrient content, is no longer present in the food, it's reached the end of its acceptable shelf life. In Australia, the requirement to add a best before or use by date to packaged foods is regulated by standard 1.2.5 of the Food Standards Code. It's called date marking of food. This standard states the legal position that defines whether a use by or best before date should be applied. So the wording in the standard is that if the nutrient levels decline to unacceptable levels in a food that's intended to form the sole source of nutrition for a person's diet, or if the food can become microbiologically unsafe before the food noticeably spoils, then a use by date is applicable. Where deterioration of a food affects consumer acceptance without impacting health and safety, a best before date is applicable. Foods with a shelf life of at least 2 years are not required to display a best before date. So the regulations clearly define when you should apply a best before use by date. Use by is for health and safety reasons. Health applies where the nutrient profile of a food that the consumer relies upon as a sole source of nutrition becomes degraded to such an extent that the nutrients are no longer present in the stated quantities. Safety applies where pathogenic microorganisms and their toxins are able to proliferate in the food to such an extent that anyone who consumes it could become ill. Where this occurs before the food noticeably spoils, a use by date is required. You'll remember from the first couple of Focus on Food webinars on basic food microbiology that pathogenic bacteria grow more quickly than spoilage yeasts and molds. And best before dates, they're primarily quality indicators. Some of the changes that can lead to a best before date needing to be applied are rancidity, changes in texture, the loss or gain of moisture, flavor changes, enzymatic browning, and yeast and mold growth. So why undertake shelf life testing in the first place? Although it's a requirement of the regulations for food to be safe when they're offered for sale, the regulations also determine at which point your product could become potentially unsafe, and you need to assign a date which it would be safe to consume within. So assuring consumer safety would be the #1 priority when setting a use-by date. Testing can ensure that the date applied is accurate rather than a lucky guess. Additionally, there are cost implications to not having an accurate use-by date. Product recalls, obviously extremely expensive, both in terms of physical cost, taking the product out of the market, but also in damaged reputation. If you supply other businesses with raw ingredients, having accurate date marking on your products will also help reduce wastage and the associated costs of disposal. Just as a short aside, food waste can be attributed to a number of factors, but incorrect and inaccurate date marking is one of them. It's sadly a significant one of the causes of wasted food. A recent government estimate puts the annual cost of food waste to the Australian economy at $20 billion. And to put that into perspective, you could build over 30 new state-of-the-art hospitals, apparently, provide free university education for 200,000 students, give $500,000 grants to 40,000 small businesses, I like that one, provide clean drinking water for the entire planet for 3 years, and stop the deforestation of the Amazon rainforest within 10 years. Oh, and build half of Donald Trump's wall. So the National Food Waste Strategy in November 2017 identified accurate use-by and best before dates as an enabler for better logistics planning and execution. This in turn could lead to reduced costs, less wastage across the supply chain. If you're interested in that document, it can be downloaded from the Department of Energy and Environment website at the link here, which will be available after the webinar as well on the replay. All waste is a cost to the businesses, so it's useful to minimize the opportunities for wastage to occur. Having accurate date marking on your products contributes to reducing waste throughout the supply chain. So on a practical basis, how do you actually go about determining a shelf life for your product? So if we break it down, there are a few stages to this process. Firstly, if you've previously produced similar products, you'll have information from that which could be useful. And perhaps the product itself grew out of a family recipe and you know intrinsically that it's good for a certain time. Secondly, you'll need to know which property of the product is likely to fail first so that you can measure or test the time to failure. This can be any one of the following parameters. It could be microbiological, chemical, or organoleptic, and that's sensory, functional, physical. Now, the New South Wales Food Authority, I recommend their website. There's a lot of really useful information on there. A lot of good tools that you can download, not just for shelf life testing, but for other aspects, you know, food safety plans, etc. So it's a good source of information. This is a chart that they developed, and it's available in their 2010 publication. The link's there on the slide, and it's all about shelf life testing. It's a simple decision tree type chart that takes you through a series of questions that you must consider before applying a use by or best before date to your product. It's self-explanatory basically. It's useful as an aid memoir when considering new products and when you're sort of developing the new products. The link will be available on the slides in the rerun. So if you can't use it there, you'll be able to click on it when you access the recording. So there are a number of scenarios for when you would undertake shelf life testing. First, and obviously, when you're developing a new product, both during the initial stages and as launch approaches, it's important to know how the product will perform under certain conditions and with potentially certain packaging types. Also, though, if you make any changes, certainly significant ones, to either the ingredients or the processes, whether you have a new supplier or new redesigned packaging, it's also important to revalidate any shelf life that you may have attributed to the product through robust follow-up testing. Also, many businesses, as part of current quality control processes, undertake regular validation testing of packaging performance and shelf life, just to make sure that everything is performing as it should. So once you know which of your product's characteristics are likely to fail first, you're ready to put together a testing program to determine how soon after production the product is likely to fail. Testing usually falls into one of two possibilities. We use real-time and what's known as accelerated testing. So real-time, as the name implies, products held at the recommended storage conditions for the expected shelf life and tested regularly to determine at which stage it fails. In accelerated testing, the product is held at elevated stress conditions and the rate of degradation measured so that shelf life can be predicted using known relationships between the acceleration factor and the degradation rate. So that involves a few calculations, a bit of working out, and some different scenarios. So, and real-time testing, it's usually conducted on short shelf life products where the storage conditions can be easily replicated. For example, keep refrigerated at 4 degrees or below. Fresh salads, great example of short shelf life products that require very precise, accurate data to support the stated shelf life. Organisms such as Listeria monocytogenes, they're able to grow at refrigerated temperatures, so a shelf life trial for these types of products would include some growth modeling for Listeria and a shelf life estimate far enough below the models to allow a margin for temperature abuse along the supply chain. The importance of rigorous hygiene practices and HACCP controls during processing are evident when it comes to ensuring that the shelf life assigned to the product is not compromised through unhygienic handling or the breakdown of controls. Post-kill step, so if you have a kill step, like a chlorine wash or a cook step, hygiene after this step is crucial to the preservation of any stated shelf life. Now, the theory behind accelerated testing is that an increase in a key storage variable will have a measurable impact on the rate of spoilage of the product. So usually a temperature increase is applied because this is the simplest measure to control in a lab setting. And by working out the factor by which a temperature increase of, say, X will affect the rate of spoilage of a particular product parameter, we can extrapolate a more accurate estimate for the shelf life of longer shelf life products and reduce the time to market for the product. An important rider to this, obviously, is that accelerated testing is not foolproof. It needs to be validated with real-time trials running concurrently, so you need to be prepared to adjust your shelf life at the end of those real-time trials. And it was sort of many years ago that product changes were uniform, but this is no longer the case. Rates of spoilage of one parameter may be constant, but there may be an unanticipated knock-on effect of other parameters within the product that reduces acceptable life in other ways. So, I mean, this is especially true in modern food production, where the rate of innovation is bringing with it ever new challenges. There are new products coming on the market. They haven't been tested in the marketplace for years, decades, like some of the more traditional products, and they're bringing with them some new issues. Label, which is sought after by clients, it's great. Consumers are looking for it. If it comes with safety and guaranteed acceptability to the customer, it's a great thing to have. But it's more important than ever to ensure that your shelf life testing and your trials are robust and supported with due diligence activities such as monitoring customer feedback, random end product testing, and real-time trials. So the process of setting up a shelf life trial. First step is to understand the product and how it could perform over time. So a large part of this, if going back to some of the earlier webinars that we had, a large part of this is tied up in the intrinsic product characteristics. So you'll remember that the intrinsic characteristics are factors such as the pH, the water activity, whether the product has any natural or artificial preservatives in it. And then you also want to take note of the extrinsic characteristics, which are the type of packaging that will be used, the gas concentration, if any, headspace, storage conditions, etc. So also included in these considerations are whether or not the product has undergone a kill step during processing. Understanding the product characteristics enables us to predict a key end of shelf life parameter, which may be microbiological, spoilage or safety related. It could be chemical, for example, rancidity or nutrient degradation, or it could be organoleptic, for example, smell, taste, appearance, etc. Does the product look like it should after 3 months? So the key end of shelf life parameter is that element of the product which appears first to signal the end of the product's acceptability to the consumer. As different people have different tastes and different expectations from products, we need to make this value something that can be objectively measured. So we apply specifications which help determine when the product reaches the end of its shelf life. For example, a microbiological specification for end of shelf life, it could be when the mole count exceeds 100 CFUs per gram. A chemical specification may be a peroxide value over 10 milliequivalents or MEX of oxygen per kilogram of fat. An organoleptic specification may include specifications such as a clear, odorless liquid. Now, this may be a useful table for you to download when the replay gets put up. It's really useful. I borrowed it from a book called Food Processing Technology, Principles and Practice by PJ Fellows, which if any of you have a Scribed account and you're a member, it's available for free on that one. It shows key spoilage mechanisms for a range of food types. So you can use this information to predict the most likely way in which your product may fail at the end of its shelf life. This can help, obviously, when designing the testing program. You don't want to be measuring the microbiology of a product that's likely to fail on a chemical value, such as rancidity. So whether you opt for real-time or accelerated shelf life testing will to a large extent depend on your anticipated shelf life, with time to market being a key business pressure point and not having the time usually to undertake real-time testing for a product if you're anticipating a 12-month shelf life. So real-time testing is the most accurate and reliable method, obviously, for establishing a use by or best before date. But when factoring in business pressures, product launch considerations, it tends to be used more for products with less than 3 months of expected shelf life. Chilled storage products generally have a shorter shelf life and should ideally be assessed using real-time testing, incorporating a range of potential abuse or worst case scenarios as well, such as elevated storage temperatures to mimic inconsistencies in the chill chain. The aim's to determine how a product performs under the conditions that it's likely to be subjected to in the real world. So when you design your testing protocol, you don't just keep it under perfect conditions and expect your product to perform like that when it's out in the marketplace. It's always good to factor in the temperature rises that you see during the chill chain on a normal basis. For example, if you're sending products out direct to consumers via a courier and they need to be kept cool, this should be factored into your shelf life trials. How long could it remain at ideal temperatures during transport in summer seasons? What about if the temperature rises significantly beyond ideal for a few hours? What impact does this have on the acceptability of the product? Asking yourself these questions and setting up tests to replicate those potential conditions could help you, certainly with looking at alternative packaging or alternative distribution models, especially if the testing results indicate that your anticipated shelf life is much reduced during these abuse conditions. Accelerated trials are best suited to mid to long-term shelf life of ambient or frozen products over 3 months. It's important to note, as I mentioned earlier, that accelerated shelf life testing is based on mathematical and statistical models, and I have to be clear about this, there is some disagreement in the scientific literature on the extent to which it can be accurately used to determine a shelf life. Numerous studies have been undertaken that use acceleration models based on the Arrhenius equation. I won't get into that here because it's just long, complex. It's basically a formula which explains the temperature dependence of reaction rates. A mathematical way of showing that when you raise the temperature of something, an observed reaction will increase in rate. But in food science, researchers have used an approach called Q10, where an increase in storage temperature of 10 degrees Celsius is utilized to observe and predict the rate of spoilage in a product as measured in one key end of shelf life parameter. So just take you through the steps to consider when planning your trials. Begin with what are the recommended storage conditions? So chilled, frozen, ambient. What exactly are you looking to test? Is it microbiological changes? Is it the nutrient profile, fat degradation, the taste, etc.? And you want to think about how many time points are actually required. With short shelf life products, you may need to be testing every couple of days initially, and certainly every day towards the end. If your time points are too far apart, you could miss the end of shelf life point and either over or underestimate the acceptable life of the product. Now, at the lab, we often get asked how many samples are required to be submitted when conducting shelf life testing. So, general rule of thumb is that you'll need at least 1 sample for each planned time point and test. Each sample should be stored under the same conditions, and ideally they should be from the same batch so that we're comparing like for like. Also, if you're running tests at normal and abuse temperatures, you'll need to factor this into the number of samples to submit. Now, I always recommend as well that you keep several samples of your product yourself under the same storage conditions as those you've submitted to the lab. So if it's a chill product, keep them in the fridge at 5 degrees C or less. And what you'll do is you'll use these as a control. So the lab will provide you with your testing results based on microchemical, etc. But you'll be able to perform your own physical examination of the products on an ongoing basis. So how does it look, smell and taste as it should? If you're submitting samples for accelerated shelf life testing, you should always keep a stock of samples under normal storage conditions yourself and submit them to the lab at the end of your estimated shelf life for the same testing as was done during the accelerated testing. And this is to help validate the applicability of any accelerated trials that were undertaken. Also important to monitor customer feedback. I can't stress this enough with any sort of new product that you're putting onto the market. If it's just launched and you've put a shelf life in that's sort of, you're thinking you can get 6 months, but you're being safe and going for 3 months to begin with, monitor customer feedback, see if there's anything in there that you need to take note of. Are there any complaints about how it tastes, looks, smells, etc., feels under normal storage conditions? So as I mentioned, you've got to ensure that your product is tested under both ideal and abuse conditions when conducting real-time shelf life studies. Abuse conditions generally include elevated storage temperatures that may variations in the chill chain. For accelerated trials, a constant temperature elevation is generally applied to the product for a specified time to determine the rate of change in a key characteristic. But as I said before, it's essential that you keep samples under standard storage conditions as well and retest them at the end of the estimated shelf life. Because what you're doing under accelerated conditions is you're determining a rate of spoilage and then you're extrapolating that out and applying it across the board to estimate a shelf life. But what you want to do is validate that at the end of the 6 or 12 months that that equation was actually correct. So how do you decide which parameters to choose? You need detailed information essentially about your ingredients, processing, characteristics of the product. If you're submitting samples to the lab and you're looking to develop a shelf life trial, we've created an online form at this link here where you can input all the product characteristics and details that you have. You can use that to submit all your detailed product information to us. It will help us to best advise you on the most appropriate end of shelf life parameters for your product. And sometimes if you don't know some of the intrinsic characteristics of your product, such as pH and water activity, it may be necessary just to get those analyzed first before we set up the trial. It helps to narrow down exactly which parameter it is that's likely to fail first and hone the testing more accurately. So a few slides ago, I mentioned the Q10 approach, also known as the rule of 10. Mentioned that in relation to the Arrhenius equation. So the Q10 itself is a factor, and it's derived from the equation R2 divided by R1, where R represents a nominated reaction rate at a specific temperature. So, and then you compare that to the same reaction rate at the temperature plus 10 degrees C. For foods, generally, there's an assumption that the Q10 factor is 2, and a lot of labs I know use this as a rough guide. But we can see from looking at a worked example in the next slide that using an assumed factor can drastically impact the calculated shelf life. It's important to note that this method's only one approach in terms of accelerated shelf life testing, and there are many such methods currently being used to estimate shelf life on a range of products, and all testing has to be product specific. No one method's foolproof. We should always bear in mind there's a very famous professor from Cornell University called Harry Lawless that likes to keep people focused on important stuff, and he said that accelerated testing is mostly useless. If it worked, you could make fine aged Bordeaux in an oven. You can't. So it's important to remember that any accelerated shelf life testing is an estimate only, no matter how accurate, how complex the mathematical models. It gives you an estimate that you can launch with, but it's important to keep monitoring customer feedback and to keep back samples so that at the end of your initial estimated shelf life, you can undertake the same testing that we did originally and confirm, validate, or reassess the shelf life that you've assigned to the product. So this slide shows a quick worked example of the cutane factor as applied to a long shelf life product where the end of shelf life parameter is mold spoilage. Please note, this is a theoretical model. It's purely designed to demonstrate how the Q10 approach can be applied and used to provide a more accurate estimated shelf life. It's not based on a real product. So we can see that the control storage temperature, T1 here, is 25 degrees C, and at time point 1, the mold count was 2. At time point 2, under the same temperature conditions, the count had risen to 100. Therefore, the rate of spoilage, R1, for this product at 25 degrees C can be calculated by 100 divided by 2, which equals 50. When we increase the temperature to 35 degrees, which is 10 degrees more, we see that at time point 1, obviously the mole count is 2, but at time point 2, the mole count has gone up to 180. So the rate of spoilage there is 180 divided by 2, which equals 90. So now we have the two rates of spoilage, R2 and R1, at different time temperatures, T1 and T2. We can work out the Q10 factor by dividing R2, which is 90, by R1, which is 50, giving us a factor of 1.8. Now 1.8 is just a factor. It doesn't correspond to any value apart from the fact that it's a factor. Having calculated the factor, we can apply it to the product stored at elevated conditions until it reaches the end of shelf life specifications for this parameter. For example, if the parameter is the mold count, and we've determined that at 1000 CFUs per gram, the product is unacceptable to the customer. So we find that at storage temperature of 55 degrees C, the product reaches 1000 CFUs per gram of mold in exactly 5 weeks. So to determine the shelf life at normal storage temperatures of 25 degrees C, we multiply the 5 weeks by 3 times the Q10 factor. So that's 1.8 times 1.8 times 1.8, giving us an estimated shelf life for the product of 29.2 weeks or 6.7 months. So just underneath here, just to compare that with what is often used, a Q10 factor, a generic one of 2. If we'd used that factor, the estimated shelf life would have been 5 for the 5 weeks, times 2 times 2 times 2, which would have been 40 weeks. So you can see by not taking the time to work out a correct factor for Q10 and just taking a generic value for Q10, we've vastly overestimated the potential shelf life on that product. So what are the potential pitfalls? We've seen how testing can help you with determining appropriate shelf life for your product. Here are a few pitfalls to avoid when setting up your trials. Firstly, and most importantly, I think actually choosing the wrong end of shelf life parameter could prove costly. For example, there's a tendency to rely too heavily on testing only the microbiological parameters of products that could potentially be likely to fail on some other factor before the microbial issues become apparent. This can be the case in products with a high fat content, for example, where rancidity may become apparent before microbial spoilage. Secondly, obviously in an effort to cut costs, not enough time points may be included in the study, and this could result in the end of shelf life event itself actually being missed when it occurs. For accelerated trials, as we saw in the previous example, the worked example, applying generic and not product-specific factors to the product could result in an over or underestimation of the shelf life. Formulation variations can significantly impact shelf life. Changes to ingredients in an established product could have a knock-on effect on the overall shelf life. If you're sourcing cheaper ingredients, they may actually be older than the ones you'd previously sourced. May not have taken this into account. So when making changes to formulation, suppliers, processes, or packaging, should revalidate your shelf life ideally, as even small changes can have an impact over time. It's also important to remember that breakdowns in hygiene or in your hygiene controls during processing can have a dramatic impact on the shelf life of your products. High yeast and mold counts from the environment post-kill step can ensure that the product is nurturing a host of spores that will be able to multiply unchecked by any other microbes. So here's just a list of information you should know about your product in order to set up the trials and pick the appropriate testing. Hopefully most of this information you'll already have. Some you may need to do some initial testing on to establish, for example, pH, water activity. With testing, any sort of testing, it's important to plan your testing early as it can take sometimes longer than you'd hope. Some businesses, certainly larger companies, elect to undertake challenge testing, and this is especially important in innovative, new, niche products that haven't really got a lot of history in the industry. Challenge testing is where the product is deliberately inoculated with a known amount of a specific microorganism in order to determine whether that organism is able to grow in the product. And you can apply a range of storage conditions to see which ones it grows best under and avoid them. It's particularly important for an organism such as Listeria monocytogenes, where there are actually regulatory requirements for testing in high-risk products, and specifications are set depending on whether or not the organism is able to grow in the product under stated storage conditions. So challenge studies can provide that information with a range of different temperature profiles, packaging types, storage conditions, pH, water activity, intrinsic factors, etc. Challenge studies can be expensive, but obviously not as expensive or damaging as a high-profile product recall due to the presence of Listeria monocytogenes. So there are a great deal of resources online that can help in determining an estimated shelf life for your product. All of the websites on this slide offer a variation on microbial growth models where you can input various parameters such as storage temperatures and formulations in order to predict growth of a range of spoilage and pathogenic organisms. They're really useful, especially when you're in the product development phase, so stage 1, stage 2 of the product development cycle. But again, it's important to remember that they only offer an indication and they can't be relied on to predict shelf life without backing that up with validated testing. Obviously, validation testing always should be conducted in real time, even if you do accelerated testing as well, with the actual end product and not the prototype. So here's just a quick example of the sort of thing that you can get from some of these online growth models, and you can see the benefit that it may have, certainly in the initial stages of product development. You can input some different factors, such as we're looking here at Listeria monocytogenes growth at stored temperature of 5 degrees C, with pH and water activity remaining constant, versus at 8 degrees C with nitrite content and 8 degrees C without nitrite in it. And you can see the variation there in the time it takes for the product to become unacceptable. So finally, just a quick word about nutrition content claims and shelf life. If you're making any claims for your product, such as high in vitamin C, you need to verify that these claims are accurate at the end of shelf life as well, not just at the beginning. So nutrients degrade in products, and the rate of degradation is not necessarily linear. So due diligence and good practice dictate validating all claims that you make on your products for the end of shelf life, as well as at the start. Now, obviously, there are cost implications for this, and not everybody's likely to do this all the time, but it's just important to bear in mind that it's a consideration, that if you are making any nutritional content claims for your products, you need to ensure that those are still valid at the end of the assigned shelf life as much as at the beginning. Okay, so thanks to everybody for attending today. See, there's a good attendance again. As always, the recording will be uploaded to Focus on Food website later. It can be downloaded and accessed along with all the previous webinars. So we've got 4 other recordings up there today. This is our final webinar of 2019, as I know everyone will be flat out for the next few weeks. So we'll return in the new year with a focus on food regulations. Keep an eye out for our emails when we come back from any well-deserved breaks. I know it's early, but I hope you all have a fantastic Christmas break, and that next year will be a very successful one for you. Look forward to seeing you next year. Thank you very much.